Hello and welcome to the next chapter in the VELOVirtual webinar series. I'm kind of reminded of an expression in the rehearsals for this one, that innovations happen at intersections. And I think that's really true of today's topic. Today, we're going to be looking at the intersection of three technologies: an energy source of the future in concentrating solar power, state-of-the-art in turbomachinery design, and then Velo3D's support-free metal additive manufacturing. And according to the US Department of Energy, Supercritical CO2, which is what we'll be talking about today on the turbomachinery side, has the potential to reduce the cost of solar power by more efficiently converting solar heat into electricity. So if you're used to photovoltaics, like my background, it's a little bit different. Here we're going to be talking about heat. But as we'll see, leveraging that power of supercritical CO2 has its challenges. You've got extremely high temperatures, pressures, corrosive environments, just to name a few. But given these requirements, manufacturing these applications can be nearly impossible up until now. And so we're going to be talking about that. It's an honor for me to introduce James Walton. James is a co-founder and vice president of Mohawk Innovative Technology. He received his BS in mechanical engineering from the University of Virginia. And I hear he's got an affinity for the Cavaliers, and his ME in mechanical engineering from the University of Florida. Go Gators, team close to my heart. Mr. Walton is a US Air Force veteran, a fellow of ASME, and he has published over 100 technical papers and has 5 patents. He's also involved in rotor dynamics research and advanced product development for over 40 years. Next is Dr. Jose Cordova. Jose is a principal engineer and program manager at Mohawk, where he heads the engineering team in charge of analysis and design of turbomachinery and other power conversion and energy generation systems. He received his degree in mechanical electrical engineering from the Universidad Nacional Autónoma de Mexico, and his MS and PhD in mechanical engineering science from the University of California at Berkeley. He has a broad background in mechanical engineering science, spanning multiple fields, including combustion, fluid dynamics, heat transfer, thermodynamics, and applied engineering mathematics. Last but not least, our own Gene Miller. Gene is a senior applications engineer at Velo3D. He joined Velo3D in 2016 as a process engineer, working on developing Velo3D's hallmark support-free metal laying processes. Prior to joining Velo3D, he has held a number of roles in positions in foundry and process engineering. And Gene has a BS in mechanical engineering from Colorado State University. So now, James, I'm going to turn it over to you.
Okay. I want to first thank the people here at Velo3D and their team for inviting us to share a little bit about what we're working on, what led us to additive manufacturing, and how it's helping us achieve our goals for the work that we're doing in high temperature heat transfer fluid circulators for concentrating solar power. What I wanted to do first then was to kind of give you an idea of how we're going to fit into the concentrating solar power energy systems, but give you the overview first of what the big picture is. So the picture you see on the right-hand side of the screen here is a concentrating solar power plant. You see all the mirrors, or what they call heliostats, which concentrates the solar energy up into a receiver here, which is the bright light. Look into the light. And then what they do with that heats up a working fluid. And there are systems out there today, and they use steam. So what they're doing is they will concentrate the energy in the receiver, as we see here, to heat up a working fluid. That would then come down and then go into a what we would call, using the heat transfer fluid, to heat up steam, which would then go to the turbine and produce electricity. But what we're looking at here is how to improve the efficiency and the quality of the output from these concentrating solar power systems. But in order to do that, we're going to be working with a more energy dense fluid, supercritical carbon dioxide. And they want to prove out, DOE does, the fundamental components and component technologies that are going to support these systems. So the system we're working on is about 1.5 megawatt thermal heat load that we're going to be dealing with. And we're going to be taking and moving the working fluid into heat exchangers and thermal energy storage. And the reason they want the thermal energy storage is that, as you can imagine, you get a max power output during the middle of the day. Well, that's not when they need the power. So in some power utilities, they'll actually say, you want me to take the power, you're going to pay me. So that's not obviously optimum use. So if they could store the energy so that they could then produce electricity in the evening hours, let's say from 5 to 11, but also have enough so that they could support the peak load in the early morning hours, let's say from 5 a.m. to 9 a.m., that's where solar power really becomes effective. And so you do need a way to store that energy. And once we prove the technology out on this smaller scale, then they want to begin to scale up to 100 megawatt power plants. A couple of the key features of the system that we're looking at is you can see the inlet pressures for that supercritical carbon dioxide, anywhere from 127 to 240 bar. And you got a variable pressure rise that might go up from 5 to 46 bar. Pressures at the temperatures at the inlet are going to be on the order of 500 to 700 C. So you can see it can be a pretty aggressive environment that we're trying to deal with here. But why then are we looking at SCO2 or supercritical CO2? Well, the key benefit there is that it's in a supercritical state, it has the properties of a liquid and the viscosity of a gas. And so that allows for extremely high power dense machines. And the benefit of that is you can make smaller machinery, smaller hardware. So consequently, total machine should cost less. But in that small package, you're going to spin at very high speeds. So the little table on the right here just kind of gives you an idea. Again, just to kind of reiterate, 500 to 700 C, 127 to 240 bar. For this machine to give us the kind of energy storage that we want so they can eventually turn it into electricity. So a couple of the challenges that we have to face here and to get the power out of this system is the very high temperatures and the wide operating range that we're dealing with. So our speeds can vary 2 to 1. Pressures are going to be varying, as you can see, from 127 to 240, almost 2 to 1. Flows are going to vary in that range. And so what we want to do here is validate and prove out the technology in a small system. But the challenge of a small system is that it makes it sometimes difficult to manufacture. And when we say small, let's talk about scale, in a sense of scale. So we're looking at a 10 megawatt type system for proof of concept prototype, of which our blowers or our compressor is about 1 megawatt thermal. Give you an idea, this is a commercial generator system. And here you look at the gas turbine generator for a 10 megawatt system, and it's about 20 feet long, weighs about the total package, which is in the upper left-hand corner and shown in the picture in the middle. You can see the size reference as well by the men that are working next to the machinery. That package is about 83,000 kilograms. So when we talk scale, how does supercritical, when we say it gets smaller, how much smaller does it get? Well, if I look at a turbine, as I see here, you see that's a half a meter, not 6 meters, or basically maybe a couple feet long. You see here, I've got maybe 1 foot long recompressor and compressor systems. So we can show scale of maybe 300 to 1 reduction, substantial reduction to the systems that we would see. So the system we're going to talk about today, we see in this picture here. This rotor system here, which would circulate the heat transfer fluid, is only 20 inches long. So that rotor you see in the bottom, this is the compressor shaft. That's only about 2 inches in diameter at the compressor wheel. This is a 100 kilowatt, 100,000 RPM drive shaft. So when we say it runs at very high speeds, 100,000 RPM and 100 kilowatt, the key component that we'll talk about today is this 3D printed volute housing. And as you'll see as we go through, it's a pretty complex assembly of componentry inside of it that makes it a real challenge to manufacture. And now let's take a look at the inside. So when we talk about complexity, what you can see going from right to left, here's our 100 kilowatt, 100,000 RPM motor. and it's got to be kept at low temperature, let's say below 150 Celsius. This is our production end. This is the end that is most concerned. And here we're running 500 to 700 C. This is the part that you see, this lighter gray part here. This is the complex piece that we're going to be talking about today. And you can see the flow path. This is where we're going to bring inlet supercritical carbon dioxide in at, let's say, 127 to 240 bar, and we're going to discharge it out here. These passages are small and quite complex in shape, and they're a spiral kind of a configuration, so it makes for a challenging arrangement. Again, here's our compressor wheel, and as you can see, very small and small passages even in the interspace between blades. So that assembly is what we're going to be dealing with and what we were looking at. So what I really wanted to show as well is that while we see the cutaway here, and we see that the machinery, here's again, our discharge and our inlet passages. The challenge is this section here has got to deal with very high temperatures and pressures. So you can see, just as an example of the kind of temperatures we're going to be looking at, this system in here is going to be glowing red hot. So we need nickel-based super alloys. We need high temperature alloys. And because the pressures are so high, we're going to need some fairly thick boundaries here to be able to accommodate the gradient in temperature that we're going to experience. So when you're making this component, that it is complex, we're also not only going to look at its capability from a point of view of technical elements, but we also want to take a look at, well, what's it going to cost? Because as we begin to scale up, and if you see on this plot here, if this is cost of the system, compressor system, as a function of the power necessary. So if I'm looking at a 100 megawatt system, I could spend anywhere from, let's say, 8 million, if depending upon which economic models you use, up to $60 million. So if I can save 5 or 10% on some of the key components and parts of the system, that's a huge saving. So because we need to get the cost of electricity down so it can compete with, conventional electricity production that's out there today, whether it be natural gas fired turbines or whether it be nuclear or whatever. So getting now into the component and how we went through this process of trying to establish this particular hardware. When we came up with the configuration, we realized that the configuration was complex in the geometry, as you can see here. And so we said, well, how are we going to make this? We said, well, let's take a look at people that we've worked with before. So we went out to a number of casting houses that we'd worked with before. And as it shows in this table over here, we went to 6 different companies and nobody would quote it. We would have to make design modifications to this hardware to allow them to cast it in a way that we could use it. And of course, by those modifications, we're going to reduce performance. And we didn't really want to give up on performance because that's going to affect the levelized cost of electricity in the final product. So we talked to companies that could machine it for us, but they were extremely expensive, on the order of 3.5, maybe even 4 times more expensive. But look at the lead time, 6 weeks. If they could have made it in casting, would have been about 6 weeks. Machining it would have been about 20 weeks. Previously, we had done some work in additive manufacturing on a recuperator that Dr. Cordova had come up with that we have patented. And in that recuperator, there were some thin sections, and that's where the additive manufacturing failed, was in these thin, unsupported sections. So we weren't too sure about it. And that particular component was made out of a stainless steel because those temperatures weren't as high as what we need here. So in this application, we were concerned. We said, well, let's take a look at additive manufacturing and see what's out there. And we saw that, we went to Velo and said, hey, they're working in Inco 718 is what we need. And so that got us started in this process. And one other thing that we were concerned about also with the casting that was really has affected us in the past. We had a complex part cast. And when we were doing some finished machining, we came across some huge internal voids. And we really wanted to avoid having voids in the part, particularly given the high internal pressures that we're dealing with. So when we were very interested in going to see what additive manufacturing had to offer. Breaking this part down a little bit more, and Gene will get into the details and some of the challenges that he experienced in laying this out. But we ended up with fundamentally 3 parts that are going to become one. This is the fully integrated part, and this is the part that's going to be manufactured in 3D. And then we had these 2 other parts machined. You slide this part in, you weld it, then you clean it up, then you slide this part in and weld it. And like I say, Gene will talk about the complexities of some of the overhangs and so forth. And so while we were quite interested in it, still we were concerned about material properties and wanted to make sure that because of the high temperature and the high pressure, and our first experience in working with additively manufactured Inconel product, we wanted to make sure that the material properties are what we would want. Particularly, we don't want to have a burst or something of that nature. So we talked to Velo about that. And we really appreciate the fact that they're so willing to work with us to try to allay some of our concerns. So they produced some samples for us, as you see in the picture down at the right-hand side. So we're not going to take a huge materials because we're all doing this on what we call our internal research funding. So we want to do enough, though, that we have confidence that we feel the process is appropriate. We want to test for tensile strength. We want to look at Young's modulus. And we want to make sure that the properties pretty much isotropic rather. So with that, we got those specimens and we had them built in different orientations. So the first one was printed up vertically. So just as you see it standing there, that's the way it was built up. And then the printed longitudinally component, which is laid here on the granite table. You can see it was built in this way in that direction. So there would, if directionality or isotropy or anisotropy would be evident, we should hopefully see that in our tensile specimens. And then we had some standard blocks made so that we could do some other evaluations of the material. We took those rectangular specimens, cleaned them up, and then had them evaluated to make sure, well, first off, is the material, does it meet the spec for Inco 718? And chemically, it does. So the table on the right basically shows you, yes, it meets the UNS specification for that material, a precipitation hardenable nickel chrome alloy. So first margin or first milestone met. The next one we wanted to take a look at, do we get good bonding internally? What is the grain? Is there orientation to the grain? And a couple of the metallographs shown here, we just took some random samples of from the material. The unetched photo shows that we had good fusion at the boundaries, and we don't have those voids and things of that nature. So we're indicative of good creep strength here. The acid etched component says there's no real directionality on the grain. So that gave us additional confidence that the material is going to be what we want and what we need. So we took those, the round bar specimens, machined them, put them into dog bone or specimens that can be put into an Instron machine to do the tensile testing. And that can be done at both, and it was done at both room temperature and near the operating temperature that we would expect to see, or 1100 degrees Fahrenheit. The table on the right shows the type, the samples, and the data that was acquired. But the details I'll show in the next slide here. If you take a look at the average of the mechanical properties, what you see is on the left table, upper left table, that's for the 3D printed values. The first column here shows the ambient room temperature, and the second column here shows the 3D printed average properties at 1100 degree Fahrenheit. We see about 29 million modulus for Young's modulus, yield strength of about 157 and 191 ultimate strength for the room temperature. Elevated temperature, as expected, we see a degradation down to maybe, like I say, 21 million modulus, 130 KSI and 156 KSI ultimate. Compared to bar stock or Inco 718, you can see in the room temperature modulus, we're basically about the same. We're a little higher in yield strength and higher in ultimate yield strength when you compare the printed versus the common bar stock. Similarly, we're higher in yield strength and in ultimate strength, but lower again in the Young's modulus, and that's kind of summarized here. And if you look at the variations you see, it's really not really, I would say, significant, given us we have a very, very small sample size. So we're very pleased that the properties are actually very pleased that we have much higher, or not much higher, but have higher strength both at room temperature and elevated temperature, where it's most important. So we're very pleased with those results, and then we went and said, let's go ahead with it. But let's also take a look at when I talked earlier about anisotropy, you know, is the properties the same regardless of how it was laid up? We see some evidence that there is a minor variation in the two axes. So if you look at the horizontal specimens in the first white column, and then you look at the vertical specimens in the second column, you can see there are some differences here. And what they turn out to be that there is some anisotropy evident. Not again substantial. It's only maybe 2 to 3% in the tensile strength, where the horizontal or longitudinal specimens do show higher properties at both ambient and elevated. And the Young's modulus is where there's a little more difference, but again, it's not at a point where it's going to affect us in this particular project. So that was very good information for us. So we go here, and what we see here now is the as printed part on the left. And then on the right, what you have is the finished part after machining, printing, and so forth, and the partial assembly of our system with our test rotor here. And with that, what I'd like to do is then pass it over to Gene to kind of go through, as we've mentioned, the build process and all that he went through.
Yeah, thanks a lot, Jim. So as Jim and Jose designed this part for optimized performance, they're faced with the reality of manufacturing this part. You know, and that's what Jim was alluding to earlier, where you have to make these compromises for the sake of manufacturability. And that's what we like to pride ourselves at Velo3D, that we can just skip that step and go right to the manufacturing and forget the compromise altogether. And this is a great example of that, where we're really taking the design intent and putting it into the part. So taking a step back, what is laser powder bed fusion? On a real high level, it is the accumulation of powder over layers fused together by a laser. And at the end of the day, these individual layers are stacked up upon themselves to make a part. It consists primarily of a piston that moves inside a cylinder bore that moves down each consecutive layer. In our case, it's 50 microns, about 2/1000 of an inch. And the recoder, in this kind of diagram, I'm showing what I like to call a dump and smear recoder. This is like a conventional metal AM powder bed fusion system where the recoder just smears the powder across the powder bed. And then the laser melts selectively the material that we want to be accumulated to create the part. And whatever powder is not fused is removed and recycled for the next build. So why do we need supports? A lot of these low overhanging features can't print on their own, especially in conventional metal additive manufacturing platforms. To exemplify this, here is a low overhanging arch type structure. If we try to print this without supports, the internal stresses and warp of the part will tear itself upward and could cause recoding to be impossible unless we put these support materials on. And that's what we're showing in the red support structures that are kind of essentially acting as anchors to keep the material constrained downward on a nominal height off of the powder bed so that we are able to continue recoding and build this structure. Now, at the end of the day, you're going to have to take these supports off. And that's fine if you can access them, you can machine them, you can maybe even break them away by hand. But if you can't get to them, in this case, it doesn't make sense to print this part on a conventional metal AM system. kind of exemplifying what you'd have to do in a conventional sense on the left here. And everything you see in red is support structures that are added to the design to enable printing. And on the inside of these volute sections, Jim was talking about the inlet and outlet volute sections. A conventional metal AM system would have to put support material here in order to have a successful print. The Velo 3D Sapphire doesn't need these supports. We have low angle processes that are applied to avoid the need for any type of support structure in these inaccessible sections of the part. So how do we do this? This is our Mike will know, our most popular question that we get asked all the time. How do we print support free? Well, the secret is really to break it down into smaller, more chewable bites. We have a preprint software called Flow that's proprietary that we developed that will recognize all of these types of features. And we're kind of calling them out on the right-hand side here. The bulk core in this part in particular is very important. We know this is a big bulky part. There's a lot of material. There's a lot of time spent lasing this bulk. And if you don't have a high throughput power applied to that bulk core, well, then it's going to take forever to print. And luckily, Velo 3D has two 1 kilowatt lasers in the Sapphire machine that we utilize at a full kilowatt. And our throughput is very fast and very high power. And I know that a lot of other incumbent systems have struggled with applying these high powers to high throughput systems. There's a lot of soot generated. There's a lot of challenges that come along with this, but we actually do it. And Flow recognizes that and applies this high throughput power or a high throughput process to that section of the part. It recognizes low overhangs, like in the volute sections where we don't want to add support material, but Flow is intuitive enough to recognize this low overhang and apply a predetermined set laser parameter to that section such that it prints support free without the need for any support material and also with a very smooth nominal surface finish. The closures, again, they get their own specific laser parameter and vertical walls are recognized by the Flow software itself. And Flow is unique in that it does offer the user the opportunity to apply manual overrides as well. If you would like to have a higher throughput, you can turn off contours. If you have small, very delicate internal channels, we have miniature processes for that. So it really opens up a lot of opportunities for the user to specifically apply these laser parameters if they deem it necessary. So here's our claim to fame, really our non-contact recoder. This is how it all started with Velo 3D. This is not a dump and smear recoder system. It does dispense a thick layer of powder in the recoating motion. And then right behind that powder dispenser, there's a normalizing blade. This blade flattens and levels out the dispense surface such that it is then approached by our proprietary powder removal tool that removes all but 50 microns of powder. So we have a nominal layer thickness every layer. And this is all quantified every layer by our height mapper. It's a structured light scanner that scans the entire powder bed surface every layer and quantifies it, and will actually detect any anomalies in the build and report them to the user. Velo 3D's, we call it a full stack solution. From start to finish, we have every tool that you would need to build a part, to prepare a part, build it, and then have a report at the end of the day. Our preprint preparation software that I talked about earlier is called Flow. It's a 3D design space where the user will import a CAD geometry, and we support native CAD like SolidWorks, Pro-E, Creo, NX. We also support XT and step files. We don't do STLs like most of the other metal AMs, but this really gives us a lot of opportunity to do some unique things with region assignment, process overrides, as well as adding support material. Now, the Flow preprint preparation software will also create the Velo print file. And that is the file that's actually loaded onto the Sapphire printer that you see in the middle here. And that's where the actual printing of the part will occur. Now, throughout the printing process, there's literally thousands of sensors on this thing gathering data throughout the entire build. And it wouldn't really mean much if you didn't have a way to compile it and make it presentable to the user. And that's what Assure, our quality validation software, does. It enables the user to actively monitor the build throughout the building process, as well as check on machine health as far as focus, powder bed quality, etc. And also has the ability to print out a PDF compilation of all of the sensor data in a coherent, easy to read build report that can accompany any part that we print on any one of our systems. So we made this video just kind of showing the print process of the Mohawk part here. And I'll pause it right here. So up into the, I believe this is the inlet. This is the first volute section, the first challenging area in this part. The build starts and opens up into this chamber, and nothing really unique happens until it closes out. And right at the top of this closure, you can see there's no need for support around the volute closure, and anything that we do add is accessible and able to be removed by machining or by hand, actually. Second volute section, this is the outlet. This is probably the most complex part of this, or portion of this part. There's a 0-degree overhang that needs to be supported and constrained in some degree. That's what you see these radial supports going around the center are going to support this internal shelf as we build upward in Z. And if you look at the volute section itself, there's no need for support inside that volute, where the post-processing would be completely inaccessible to remove anything. So we print upward into the bulky section of the part, and that is where speed is the biggest winner. Being able to apply our 1 kilowatt lasers to this process enables us to print this part very quickly and effectively without any of the lack of fusion porosities or voids that would degrade the material properties. Here's a video. This is right from our height mapper structured light scanner, showing the entire print from start to finish, layer by layer, showing the volute sections, the closeouts, and then the bulkier sections that print with this this high power 1 kilowatt process. And here you have it. This is the finished part. At the end of the day, this is after post-processing. The discoloration that you see is part of the heat treatment process. And then the internal machining is all done on this part. The pen is there for scale to really give you an idea of how big this part is. And at first glance from the outside in, it doesn't look that complex or challenging, but really when we look at the inside of this part, that's where the magic happens, and that's where we minimize the compromise that Jose and Jim need to make for their application. And with that, I think I'll give it back to Jim to wrap things up. Go Rams.
Okay, very good. Thank you, Gene. Okay, so in summary for us, the thing that we see is the high power density of supercritical CO2 does offer substantial opportunities in power and even aerospace applications, but it's not without its challenges. For example, as you see here, once you start getting things smaller, while you have more opportunities, like I said, is in aerospace, but the problem might be that you have more challenges. For example, we're looking at very small passages, and it may eliminate other processes. For example, we found we couldn't do the casting without compromising the performance of the part. And the reason we're going with Inco 718 is because we have a high temperature, high pressure, corrosive environment. Supercritical CO2, if you get a little bit of water mixed in, which is possible, you can have what they call carbonic acid, which is a corrosive environment. So the other part that's challenging with Inco 718, it's a very tough material, but it's very, very tough to machine. And that's why it takes so long and was so expensive to make a part out of it. The other facet, we were pleasantly surprised to see that Inco 718 in additively manufactured parts is much further along than we realized when we first got into this project. And but still, we wanted to make sure we had a good handle on material properties, and we're very pleased to see that they did meet what we were looking for. And the directionality is some there, but it's not a major concern at this point. Another key feature that we found is that when we go to additively manufactured parts, we can get some consolidation, reduce parts count. It's going to reduce the cost of the part, but also from these very high temperature and high pressure systems, if we can consolidate more parts into a single, we don't have to worry about leakage because we have many more interfaces and joints that might need to be integrated into the system. So there's just a tremendous benefit that we saw with this, and we just really appreciate this opportunity to share this info with you today. And Mike, I'm going to turn it back over to you.
All right, thanks. So there actually was a question about the blades and whether we tried to print the blades. I would just say stay tuned. We've got something in store for you coming down the pipeline. So timely slide there.
So was that the blades in the compressor system, or was that the blades in your processing equipment? I don't know. I just assumed that it was. I thought it was the blades in the compressor too. So, but anyway, stay tuned.
Yeah.
Yeah. One final thing we did want to do is acknowledge the support. As I said early on, this is part of a Department of Energy sponsored activity, this was a competitive activity. We were able to win, and we want to acknowledge also our program managers at the Department of Energy, VJ, and Mark, for their support and technical input during the entire program. And that's they've been very good to work with and collaborate with on this activity.
Okay, so we do have a number of questions that have been coming in. And we're going to just kind of dive into it as time allows. Kind of excited to see some of the answers to some of these too. But since we have so many, I'm just going to get started here. There's one about the acronym HIP. Maybe you could talk about what that means.
Yeah, sure. I can take that one.
You want Gene? Yeah, I figured Gene would. Yeah.
This is a process. It's called hot isostatic press, and it's a process that really helps eliminate subcontour porosity and especially lack of fusion porosity that could occur in some cases. This is especially used for aerospace or flight components, flight hardware, that we really just want that warm and fuzzy feeling that all of the porosity is out of this thing. We don't have internal stress concentrations that could cause a fatigue failure. So what the process is it's an inert environment, typically argon, very, very high pressure at a high temperature, so that the metal becomes a bit malleable, and that pressure kind of squeezes in on the part and just eliminates or minimizes any internal cavities or voids that might occur. It's something that's done just kind of as, just a fail-safe in this particular application.
I think a point that I think had been made earlier, Gene, that you mentioned, is that even in the HIP process, though, we don't see a dimensional change in the part, because that was important to us to know, what impact that might have on what we would have to do from a machining and correction point of view.
Yes, that's correct. It's a micro porosity change, not a macro part change. You don't see a significant change in the overall dimensions of the part. That's correct. Thanks for adding that, Jim.
Yeah.
And was hipping used because it was part of the traditional process, or was that something that was just used for 3D printing?
Well, I mean, HIP is used in a lot of different materials. I mean, I know they HIP ceramic materials when they fabricate those for densification, and that sort of thing. So I think it's a fairly commonly used process.
Yeah, and I would just add that in particular for our application, since we're dealing with such extremely high pressures, the possibility of a micro void or a micro cracks existing within the material matrix is what we were trying to completely eliminate as a possibility. So we figured it was a good, as Gene said, a good fail-safe step to take.
I had a lot of questions on the lasers, so I kind of wanted to just deal with that as a category. So getting into the lasers, what's the density that's achieved with the kilowatt lasers?
So we advertise 99.9% dense material that's printed, and that's across the board for all of our processes. if you take a microstructure of any area, it should fall into this 99.9% dense. That being said, if you do zoom in really, really far on a void, that does change. But if on a macro level, the overall porosity is 99.9% dense.
And what would be the optimal laser power, or how many lasers would you recommend? Which is an interesting question. I'll let you handle that one.
Well, I know right now the metal AM world is faced with something I've heard coined by some of my colleagues as laser wars. You have a lot of these machines coming out with 8 lasers. Oh, well, they got 8 lasers, we're gonna need 12 lasers. Okay, all right, more is better. Well, I'd like to believe it when I see it. And the problem that comes with lasers is more problems. More lasers, more problems. So really, you can say all you want about how many lasers you're going to put into the system, but at the end of the day, can you get it to work and work well? And I think with what Velo has achieved with 2 lasers, we're about to put into our 8 laser system and really go through the trials and tribulations of qualifying and quantifying all the problems that we see, and having an effective laser system. So whether you have 8, whether you have 12, whether you have 90, it doesn't matter if it's not going to work. So really, yeah, you can have higher efficiency and higher throughput with more lasers, but it's going to come with a lot more challenges.
Also in the laser category, how important is laser power to the final quality of the part?
Well, that depends on a lot of things, actually. It's you can throw down a lot of power at the powder bed, but if you don't have the proper chamber flow to remove the soot that's generated, you're going to occlude the beam and have a poor lasing condition at the powder bed. And that's something that a lot of incumbents struggle with, is flow in the chamber. It's what has been a limiting factor with how much power they can put in their bulk core processes. Velo has done a whole lot of work in process development on flow, and really quantifying the extraction of the soot such that we don't have a bad lasing condition at the powder bed. So you can throw down as much power as you want, but the question is, can you get the soot out of the way? Do you have problems with the optics overheating? It's really, you have to tailor your process to have as much power and as much throughput as you can and still produce good dense material.
I have a couple questions on some of the test data. And maybe Jim, this is for you. What do you think accounts, or Jose, for the greater yield strength and ultimate strength of the printed parts versus bar stock? Do you have any theories on that?
Well, I'm seeing Jose is also thinking about it too. So maybe between the two of us, I think one of the things we tried to caution here is, again, remember, this is a very limited data sample set. And the percentages were small. So I think if you get to a much larger data set, you might find that there really isn't that substantially different properties than what you would see. I mean, 6 samples, is a very small data set. As far as the changes from published data, I don't know, Jose, if you have additional comments and thoughts.
All I can tell you right now is that as a follow-on to this project and part of the to stay tuned, our
teaser.
Yes. In the next project, where we will eventually show you how we have collaborated with Velo in printing actual impellers for blowers, we expanded upon the tensile and mechanical properties research on a much larger batch of dog bone specimens. I believe we have something like 96 specimens altogether under a full range of conditions and printed in 3 axial directions. And what we are finding is that the mechanical properties remain perfectly comparable to the material properties reported in the literature for bulk materials. Why the similarity? We honestly expected to see a slight degradation simply because of the granularity of the process, but my only speculation is that precisely because the material is deposited on such a detailed microstructure, grain by grain, you may actually be achieving a level of fusion or of homogeneity that while we assume happens in, say, the cold rolled or on the rolled alloys, there may be slips or microfractures or dislocations in the material structure, in the crystalline structure, that are basically gone or eliminated during the fusion process with the laser. So again, this is just speculation. It's very early on, but we are seeing that at least the 3D printed material is comparable, and in some instances it's even stronger than the bulk counterpart. So again, something that will we will only resolve as more materials are 3D printed and explored in this manner.
So, question on the design. Did you have to make any redesign accommodations to fit the 3D printing process?
Actually, I would like to take this one, Jim. And the answer is really no. We would have had to make severe accommodations for the machining and for the casting approaches. So this aligns exactly with what Jean was saying, printing with or manufacturing with a compromise, I think was the statement, right? We presented you guys with the design as it came out of our aero design team CAD, and there were basically no changes made. You just printed it.
A couple questions here on the powder. So what is the D50 powder diameter?
I think they're looking for the powder particle size distribution. It's a standard particle size distribution powder bed. We take a bulk powder distribution and put it in the machine. We're not doing any tricks with stratification of the powder. We're not changing the particle size or anything like that. All it is just a typical laser powder bed fusion powder sprinkled across the powder bed, and using our non-contact recoder is where the magic happens, and our specific laser parameters. The powder's particle size distribution is completely unaltered in our process.
And how critical is the incoming material in terms of particle size?
Critical as far as chemistry, it's vital. You have to have the specific chemistry in the powder to make the alloy at the end of the day, and that's what Jim was. The first check one of the first checks that they checked was chemical composition of the material. Is it Inconel? Is it age hardenable? And that is fundamental to the powder coming into the system. Now, we do recycle our powder in our machine in the Sapphire. However, it's always under an inert environment, and we check our material properties and chemical compositions over time. We haven't seen a degradation in that, especially in Inconels that we've been printing for years now, where we never really have to extract all the powder and put virgin powder in. We just keep reloading it, and we're able to maintain that that tight chemical composition to be in spec for Inconel 718.
And this is more for Jim and Jose. Have you considered other materials like Hastex, for example?
Yes, short answer is yes. Inconel 718 is particularly amenable for the supercritical CO2 application. It behaves very well under the high temperature corrosive environment, and therefore we did not have to deviate much from what we would have normally used. But in particular for the impeller project, as you will see eventually, we did consider multiple other alloys, including titanium, which you guys print, Rene 41, which I believe would be at this point custom material, kind of tailored for us. I don't think it's one of your normal stock materials.
Right.
But depending, of course, on the temperature and, or rather the dependence of the stress strain and modulus of elasticity curves versus temperature, we have to, choose different materials accordingly.
Yeah. I mean, another material we're even looking at might be, I know Rene 95 is a powder metal, so that might be something, I don't know if that we would consider. But yeah, in these very high temperature uncooled turbines, we're looking at small gas turbines with very high turbine inlet temperatures. So yeah, those other materials are under consideration. Yeah.
There were some questions on the Assure and the metrology, and there was a mention to how many sensors that are in the Sapphire.
So there's a primary group set that we report, as a mainstream portion of the build report, and that's about 10 sensors. There's oxygen in the chamber. There's powder bed protrusion height. There's recirculation filter delta P. There's remaining powder. The really obvious things are what is fed to the typical user. In the machine itself, there are literally thousands. I don't know the number off of my head, but it is a slew of sensors monitoring and measuring everything behind the scenes. But the main sensors are what's displayed on the Assure build report, as well as what can be interactively accessed by the typical, customer interface.
There were a couple of comments on, the porosity and the sealing with the HIP process. One of them was regarding HIP using high temperatures. Do we see any deformation of the part?
No, that's what we mentioned earlier. This any macro deformation of the part is not significant, especially on a big bulky part like this. We didn't detect any dimensional abnormalities after hipping. And correct me if I'm wrong, guys. There was no noticeable difference.
No.
Yeah, I don't believe we saw anything in metrology.
No.
And a follow-on, does that mean the Sapphire is capable of printing pressure vessels that seal in fluids with minimal post-processing?
Oh yeah, that we have another webinar. I think that was chapter 2 or 3 in our webinar series. Mike, I'm sure you can point them right towards that. It's on YouTube.
We'll get you that link. So you mentioned before about upward warpage of parts. And maybe you could talk about what that is. Is that because of contraction while cooling?
Yes, absolutely. So if you think about it, picture each layer behaving as a liquid, a very hot liquid molten metal. Now that solidifies. It's still very hot, but what does metal do when it cools? It contracts. And each layer, it solidifies, cools, and contracts. Solidifies, cools, and contracts. And every layer, this propagates in Z. So it only gets worse and worse over time. And we have specific laser parameters that minimize that warping. So we can get away with bloody murder compared to a lot of our other competitors out there. But we're still faced with the same physics and challenges, which is why these volute sections are very helpful in the geometry that they grow at. They grow inward and onto themselves. So that stress compiles around the ring of the volute and helps pull the part inward and downward. So we can really print these inward growing sections all day long without any added support material. Another good case for the pressure vessels as to why we can print those without any internal support.
And is there any preheating of the powder bed to deal with the stress?
No, we have explored that and we didn't really see a huge benefit in doing so. That being said, the chamber does heat up to some degree. It's a kilowatt laser, so there's a lot of heat being thrown down, and the substrate of the part does naturally heat up with the laser powder bed fusion process, but that specific temperature depends on the nature of the part. Big, chunky, beefy part is going to have more energy thrown down, so it's going to run hotter than, say, a little thin wall process that doesn't melt a lot of material.
Okay. And more for Jim and Jose, what was the total time for development of this, maybe from design to manufacturing?
Jim, do you want to take this one?
Yeah, I think the time on that one was, I want to say, it might have been from design to talking with you guys was on the order of like 9 months. Might have been in that range. Because we started with a clean sheet of paper, and all we were given was, here's the mass flow, here are some pressures and temperatures, and the pressure ratio that you have to get to. Give me a machine that'll do that. And so with that, we had to just basically come up with how are we going to even put a machine together that can do it. how we're going to drive it, and so forth. So probably on that order of 9 months. And then, like I said, the big surprise to us, because at that stage we were actually running a little bit behind schedule, so we were quite concerned about turnaround time. And when we saw 20 weeks coming out of a machined component, that was real cause for concern. And then, so when we saw that your turnaround time was so much quicker and cost competitive, et cetera, we decided to press forward with it. Even with our concerns about material properties, which we got to go ahead from our DOE sponsors to, yes, take a little bit of the time to take a look at the materials. So they did allow us to do that as well. Jose?
Yeah, I just wanted to add that typically in the development of a system like this, as you said, we start from a blank sheet of paper, and from customer specifications to system, the bulk of our time is usually consumed with the development of the rotating elements, the shafts, the impeller, the motor, the coupling, the bearings, and the housings are typically afterthoughts. So we got to a point in the project at which we're saying a little behind schedule, and assuming that we would have housings in short order, and the shock to find exactly that optimistic 20-week time frame. That was an optimistic time frame. In reality, so the turnaround time in between, we would have been looking probably at twice that ultimately to have a part in-house. And the fact that Velo came through so quickly was really a lifesaver for the project timeline.
And Gene, what was the roundabout estimate print time on this one?
I think the print was 2.5, maybe 3 days of actual printing. The lead time comes in from engineering design, pre-print design, slicing, and then post-processing. I believe we heat treated this one in-house, stress relieved it in-house, EDM'd it from the plate, and then shipped it. So all in all, everything lumps together to about a 2-week lead time typically for this type of part.
So, and print time sounds like it's really a small percentage of that.
Yeah. I mean, printing, and especially this part, is really helped by that kilowatt bulk core throughput process. It's a pretty quick print for how beefy and chunky it is.
All right, let's see. Still getting more coming in. Is the design stackable? I'm not sure if I'm reading this right, or does it make more sense to scale it up if you needed, I guess, more power?
So you could, oh, sorry, go ahead.
I'm sorry, is this an aero or a process type question, or are we talking about the 3D printing effort?
I think we're talking about the size of the assembly. That's my assumption going into it, is we're talking about the size of the assembly.
Yeah, from the one point of view, I guess from a stackability point of view, I mean, there's a couple of process or approaches one can take. If you're going to go up in, let's say, a small change in the system power output, sometimes it makes sense, particularly if you have a system that's going to have variable power, might make sense to use multiple units side by side. So in other words, I can support 3 and 5 and maybe 7 megawatt systems, maybe with multiple units side by side. You start getting bigger, then you start wanting to say, no, we want to scale up to a larger machine because costs eventually are a factor in that. And several other issues that, total mass flow and the piping and everything, pull it all together, it gets a little more complex. So, beyond a few units, set up side by side. And that's a philosophy that's used. If you look at Capstone and their micro turbines, right? They got a 28, they got a 60, and they got a 200 kilowatt machine. So if you want a megawatt, you get 5 of their 200s, and there's some redundancy. That redundancy in some cases is very good. Right, because if one goes down, you don't lose 100%. So those are the things that you think about when you start looking at scaling up as to whether you want 1 or 2 or 3, 4 units side by side, or whether you want to just scale the whole machine up.
And Gene, there's one about powder removal from the part. What do you do to prevent powder being trapped inside the part?
So it's something that you need to be cognizant of when you do your preliminary design layout. We bring parts into flow, and in flow we can add support structures, and we can also add perforations. We call them powder relief ports. These are all added and kind of need to be taken with a grain of salt as we prepare the part for printing. So it is something that we are on the lookout for constantly in parts that we print. We want to avoid trapped volumes of powder that are inaccessible. We need to add holes in order to get the powder out before moving to any type of heat treatment or EDM process.
And you mentioned before about supports. How do you go about deciding where to add supports or where you're going to leverage support-free capabilities?
Sure, that's a good question, and it comes with training. Some of our rules are similar to incumbent metal AM design rules. However, there's some that we don't have to follow at all, and then there's some that are different, and that comes with training and experience. Which, if you wanted to print a part on a Velo 3D system, we would help explain exactly the case for each support that we need to add to a certain structure. But ultimately, it comes down to experience. We have a whole slew of contract manufacturers and customers who are at that level now. But really, in order to explain each case, it would take experience to obviously notice it and apply the proper support.
What kind of techniques would you use for support removal? And could you apply them, like what you said, the internal volute section? It was really looked inaccessible.
Yeah, so in some of the really tight corners of the volute, I added a couple of thin pin supports. They're like toothpicks practically. You can get in there with a chisel or a pair of pliers and just break those right out. I did mention earlier there was a 0-degree step on the inside right below the top volute, the outlet, and that had some radial wall supports going around the circumference. And I was able to get in there with even a pair of like a screwdriver and just kind of pop them out one by one. So there's supports that are able to be removed by hand. There's supports that are that require a machine tool to actually remove.
All right, I just noticed we're actually running 5 minutes over. We do have a couple more questions, but just to respect everyone's time, we're going to go ahead and conclude the session. If you do have questions or you want to follow up with us, please send a note to info@velo3d.com, and we'd be happy to reach out to you. Sorry, we weren't able to get to everybody's questions. Looked like there were a lot of them online. With that, are there any closing remarks from the speakers? And Jim, I'll start with you.
Again, I just want to thank the whole team at Velo 3D for the collaborative effort that we were able to pull together. Working with us to get the material coupons, working with us to get the parts done in time, and so forth. And just was a great opportunity, and we see a lot of potential in the future. So it really did help us open our eyes and allow us to take a look at where we can go in the future. And as Jose said earlier, we've got this a little bit of a teaser in his program that's looking at these this rotating group elements now. So we're quite excited about this whole technology. Jose, you want to add?
Yeah. I would just like to add that as a turbo machinery designer, the feeling, it's a liberating feeling to have new manufacturing techniques available. Traditional methods have ultimately yielded the optimal or the maximum performance they are capable of, or that we can deliver through manufacturing via traditional machining and casting method. And simply the new versatility that we have at our fingertips with the new geometry that we can achieve, and the higher blade counts and the weirder blading angles in our impellers and turbine wheel, and also the potential for internal cooling of otherwise impractical internal passages inside the rotating systems. It's opening a field of possibilities to us, and we are planning to leverage them all and we're already talking to some of your guys at Velo on what we're gonna do next in the upcoming future. So this has been, as Jim said, very eye-opening, and it's creating a new branch of development for us. So very excited.
And one other, if I can add, just one other final comment there, Mike. And I think one of the things I think that Jose was touching on is, and part of the company motto is that engineering is man's mind mirrored in his civilization. So the fact that we can imagine things and then produce them without compromise has been that's been really an eye opener.
Awesome, thank you. Gene, do you have?
Yeah, for me, this is I know the global thought of, hey, manufacture without compromise is really great. It's something that really hits the home for me more than just, what we're capable of. It's what I can do personally for our customers. My experience in the foundry world was, nope, can't do that. You got to go back and fix that. I can't do that. Go fix it. And that was my job. I got pats on the back to tell people no. So for me to be able just to say like, yeah, sure, I got you. No problem. Let's print it. That is something that I'm really passionate about. And I really, really enjoy companies like Mohawk specifically, where, they're really pushing the boundaries of the technology and what we can achieve as a whole. So really, again, this just hits the home for me.
Great. Thank you all. Great job today. And thank you to our viewers for joining us today. And we'll let you guys go, and stay tuned for the recording.
Beauty. Thank you.
Thank you.